I was saying to you, essentially there's really only two techniques for integration: substitution by parts. So let's look at this idea of by parts. This is when we use it. You've got a product of two functions and neither is the derivative of the other. So we can't do a simple substitution because we can't create that situation of derivative times function. So that's when we use parts. That's how I write it. You see it in different notations, but I write it like this. So integral of u to v is uv minus integral of v to u. I'm going to prove it. It's also known as the reverse product rule, because essentially it comes from the product rule. So let's write the product rule down in this horrible form that I hate. So d dx of uv would be u times dv dx plus v times du dx. Okay. So we know that to be true. Well, if I was to integrate everything with respect to x, so on the left hand side we now just have uv, but on the right hand side we have this interesting expression. Again, not notation I like seeing normally, but as we're talking about functions rather than those pronumerals being pronumerals, we can sort of get away with this. The dx's, if you like, cancel. It's just like a fraction, and we end up with our formula, rearrange it, and there it is. So that's where it comes from, basically. So integral of u to v is uv minus integral of v to u. So essentially we're integrating a product of two functions. One of those functions will be u, one of those functions will be dv, and we need to make a choice which is which. How to do it? Well, when you're making a choice, the function that you want to make u, basically you pick something that when you differentiate it you get a simpler function. You're trying to make the problem simpler for yourself. And the dv, because we're going to end up integrating dv, so it has to be something that we can integrate. I mean, if we can't integrate it, there's no point choosing it for dv. Let's just do a stack of examples. So something like this: x times sine x. I mean, there's no way I can do a simple substitution. So I've got to choose one thing to be something that I differentiate, makes easier. The other thing I can actually integrate. Well, I can integrate both of those things. But when I differentiate x, that's certainly going to make life easier. So if u is x, then du is dx. So it's sort of like integration by substitution, but we're setting it up for two functions. The dv then would be the sine x, so now I'm going to integrate to get the v, which is minus cos x. So now I can substitute in u times v minus the integral of v to u, but minus minus becomes a plus, and the actual integral that I have to do now is nice and easy. It's just the integral of cos x. So integrate cos x, we get sine x, but I've rearranged it so the positives first. So on the right hand side here, just like when you're doing an integration by substitution question, you write down what your substitutions are going to be. Okay, so over on the right hand side, and make it clear what your substitutions are. Don't just write them down and hope they understand what you're doing. Make it clear, this is what I'm substituting. Let's do this one, log x. You go, hang on, whoa, there's only one function there. Well, actually there's two functions there. It's just one of them we didn't write down, because in algebra we don't normally write the number 1 down. But that constant 1 is a function. So when we get something we can't integrate, well, that forces my hand. U therefore must be log x, because I can't integrate log x. If I could, then I'd just write the answer down, because that's what the question is. Du becomes dx on x, therefore dv is just the dx. So v is x. So we get uv, x log x, minus the integral of v du. Well, the x's cancel and I just get dx. A lovely little integral. It's very simple. Integral of dx is x. So there's that one I'm saying to you, just remember it. It's a lot easier, just remember it. So x log x minus x, but that's where it comes from. Let's do a definite one. So the integral of x e to the minus 7x. Well, I can integrate both of those. That's not an issue. But differentiating exponential really doesn't make life easier, because you still have the exponential in it. So again, it makes sense to make u equal x for this one. So du is dx, dv therefore is e to the minus 7x. Integrate that, I get minus the 7, e to the minus 7x. Let's sub it in. Now, when we sub in, we've got a definite integral, so that uv part we put in square brackets, same as we do when we normally integrate, and put the limits on it. So I'm going from 0 to 1. And then my integral becomes plus 1/7 e to the minus 7x. Now you have a choice. You could do your substitution for the first bit now if you wanted to, or you might want to leave it to the end because they're going to have the same limits anyway, so up to you how you want to do it. I've left it to the very end. The second one becomes minus 1 on 49 e to the minus 7x. Now let's substitute in the 1, substitute in the 0. There's our answer. This is a good one, because alright, I can integrate both of these things. If I differentiate, I want to make it simpler. Well, if I differentiate e to the x, I get e to the x. I haven't really made it simpler. If I differentiate cos x, I get minus sin x. I haven't really made it simpler. Well, I just pick one. So I went with e to the x. Probably went with e to the x because when I differentiate it, it stays positive, and when I differentiate cos, I get a negative sign. That's the only logic I can think of why I went that way. V then becomes cos x. V is sin x. Okay. So we get uv, e to the x sin x, minus the integral of v du. I haven't really made life easier for myself. So I'm going to have to do it again. But here's the thing. Whatever decision I made the first time, I've got to make the same decision the second time. Because if now I had say u equals sin x, I'm going to just end up in a circular argument and I'll get some sort of crazy statement like 0 equals 0 or something like that. So I've got to stick with the u equals e to the power of x. Du then is e to the x dx. dv is sin x, so v is negative cos x. Alright. This is where we've got to be careful because we've got all sorts of negatives happening here now. E to the x sin x, that stays there. But it's minus uv, so minus uv, I'm looking at the wrong line. That's the other thing I've got to be careful with. Minus uv, so minus becomes a plus, minus the integral of v du. But it's minus. See what I mean? Got to be real careful because you're saying minus becomes a plus, but then times that it's now back to a minus. So I've got minus e to the x. Hang on, now I'm back to where I started with. But that's where we now look at it and don't think of it as lines are working out. We think of it like it's an equation. So I'm going to move that integral of e to the x cos x to the other side, and I go 2 lots of the integral e to the x cos x is equal to that. Divide by 2, whack in the plus a c because it just should be there somewhere, and we have our answer. Now sometimes people look at this and they think, well hang on, we actually haven't done any integration. Well you have over on the right hand side when you're working out your dv's and all that. You've done your integration there. So that's the idea of integration by parts. We will now see it in other things we end up doing, but that's it.